For motor short circuit and ground fault protection, circuit breakers must comply with UL 489, which is the standard for molded case circuit breakers and circuit breaker enclosures, and UL 1077, which is the standard for supplementary protectors for use in electrical equipment. It's important to understand the differences and appropriate applications of these two standards. UL 1077 on its own does not meet the requirements for motor protection. However, a UL 1077 device can be used for motor protection if firstly the motor is part of a machine that has been tested and listed under UL or a similar standard, or secondly, a UL 489 listed circuit breaker is installed upstream of the UL 1077 device. There is potential confusion regarding voltage ratings. A circuit breaker rated for 480/277 volts is not necessarily suitable for all 480 volt applications. The voltage rating of a circuit breaker refers to the maximum voltage it can handle without tripping. For a 480 volt motor, a circuit breaker rated for 480/277 volts is generally sufficient. Manufacturers may sometimes use misleading terminology and ratings on their circuit breakers. For example, a circuit breaker may be labeled as a miniature circuit breaker or supplemental protector, but it may not be listed under UL 1077. It is always important to carefully review the circuit breaker's specifications, including its UL listing, to ensure it meets the required protection standards. For a 480 volt 3-phase servo motor with a full load current rating of 40 amps, one potential option is the Siemens Centron 3V@1T1. This is a UL 489 listed circuit breaker with a current rating of 40 amps and a voltage rating of 480/277 volts. Remember that the information provided is for general guidance only and should not be relied upon as a substitute for professional electrical advice or the applicable codes and standards. Always consult with a qualified electrician for specific application requirements. Let's delve deeper into the specifics of motor protection using circuit breakers, clarifying the standards, ratings, and practical considerations involved. We'll break down the key aspects to ensure a comprehensive understanding of this critical electrical safety topic. Firstly, we need to discuss UL 489 in greater detail. UL 489 certified circuit breakers are designed for branch circuit protection. This means they are intended to protect the wiring and equipment downstream from overcurrents and short circuits. These breakers are tested to rigorous standards to ensure they can safely interrupt fault currents and prevent damage or hazards. The UL 489 standard covers a wide range of circuit breakers, including those used in residential, commercial, and industrial applications. These breakers must meet specific requirements for interrupting capacity, voltage rating, and other performance characteristics. Secondly, let's examine UL 1077 supplementary protectors. UL 1077 devices are intended for supplementary protection within equipment. They are not designed or tested to the same rigorous standards as UL 489 circuit breakers. UL 1077 protectors are typically used to protect individual components or circuits within a larger piece of equipment. They are not intended to be used as the primary means of overcurrent protection for branch circuits. The key distinction is that UL 1077 devices are intended to protect equipment, while UL 489 circuit breakers are designed to protect the entire branch circuit. The use of UL 1077 devices for motor protection is a complex issue. While UL 1077 devices can be used in motor circuits, they must be properly coordinated with upstream protection devices. In general, a UL 1077 device should only be used for motor protection if it is part of a listed assembly or if it is protected by a UL 489 circuit breaker upstream. The upstream UL 489 breaker provides the primary overcurrent protection for the motor circuit, while the UL 1077 device provides supplementary protection for the motor itself. Another critical aspect is voltage ratings. Circuit breakers are marked with voltage ratings that indicate the maximum voltage at which they can safely operate. It is important to select a circuit breaker with a voltage rating that is appropriate for the application. For example, A circuit breaker used in a 480-volt system must have a voltage rating of at least 480 volts. The voltage rating of a circuit breaker is not simply a matter of matching the system voltage. It is also important to consider the type of system grounding. In a 480/277 volt system, the neutral is grounded, and the voltage from phase to neutral is 277 volts. The voltage from phase to phase is 480 volts. A circuit breaker used in this type of system must be rated for 480/277 volts. A circuit breaker with a voltage rating of only 480 volts may not be suitable for use in a 480/277 volt system. Another area of concern is misleading terminology and ratings. Manufacturers may use different terms to describe their circuit breakers, which can be confusing. For example, some manufacturers may refer to their UL1077 devices as miniature circuit breakers or supplemental protectors. It is important to carefully review the product specifications to determine the actual listing and rating of the device. One potential issue is that some manufacturers may claim that the circuit breakers meet certain standards, even if they are not actually listed by a recognized testing laboratory. It is always best to use circuit breakers that are listed by a nationally recognized testing laboratory such as UL. These laboratories test circuit breakers to ensure that they meet the applicable standards. Let's consider an example of a 480-volt three-phase servo motor with a full load current rating of 40 amps. In this case, you would need to select a circuit breaker with a current rating of at least 40 amps. You would also need to select a circuit breaker with a voltage rating of at least 480 volts. A suitable option might be the Siemens Centron 3V-AP21, which is a UL489 listed circuit breaker with a current rating of 40 amps and a voltage rating of 480/277 volts. However, it is important to verify that the circuit breaker is appropriate for your specific application. You should consult with a qualified electrician to ensure that the circuit breaker meets all of the applicable codes and standards. There are several other factors to consider when selecting a circuit breaker for motor protection. One factor is the motor starting current. Motors draw much higher current when they start than they do when they are running. This starting current can be several times the full load current of the motor. The circuit breaker must be able to handle this starting current without tripping. Another factor is the motor service factor. The service factor of a motor is a measure of its ability to handle overloads. A motor with a high service factor can handle larger overloads than a motor with a low service factor. The circuit breaker must be sized to protect the motor against overloads, taking into account the motor's service factor. Additionally, let's consider the concept of interrupting capacity. The interrupting capacity of a circuit breaker is the maximum amount of fault current that it can safely interrupt. It is important to select a circuit breaker with an interrupting capacity that is high enough to handle the potential fault currents in the system. The available fault current at a given point in a system depends on several factors, including the size of the transformer, the impedance of the wiring, and the presence of other equipment. A qualified electrician can calculate the available fault current at a given point in a system. Also, consider the coordination of circuit breakers. In many cases, multiple circuit breakers are used in a system to provide overcurrent protection. It is important to coordinate these circuit breakers so that the breaker closest to the fault will trip first. This prevents the entire system from shutting down in the event of a fault. Circuit breaker coordination is a complex topic that requires specialized knowledge. A qualified electrician can help you coordinate the circuit breakers in your system. Let's delve a bit deeper into the practical aspects of selecting and applying circuit breakers for motor protection, considering some real-world scenarios and best practices. Firstly, it is crucial to understand the motor's nameplate information. The motor's nameplate provides critical data, including the full load amps FLA, the service factor SF, the horsepower HP, and the voltage rating. This information is essential for selecting the appropriate circuit breaker size and type. The full load amps FLA is the amount of current the motor draws when operating at its rated load. This value is used to determine the minimum current rating of the circuit breaker. The service factor SF indicates the motor's ability to handle temporary overloads. A motor with a higher service factor can withstand larger overloads for a short period of time. The horsepower HP rating indicates the motor's mechanical output power. The voltage rating specifies the voltage at which the motor is designed to operate. When selecting a circuit breaker, it is important to consider the motor's starting characteristics. Motors draw a significantly higher current when they start than they do when they are running. This inrush current, also known as locked rotor current, can be several times the motor's full load amps. The circuit breaker must be able to withstand this inrush current without tripping. There are different types of circuit breakers that are designed for motor starting applications. These breakers typically have a higher instantaneous trip setting, which allows them to handle the inrush current without tripping. It is also important to consider the ambient temperature when selecting a circuit breaker. The current carrying capacity of a circuit breaker decreases as the ambient temperature increases. If the circuit breaker is installed in a hot environment, it may be necessary to derate its current rating. Derating factors are typically provided by the circuit breaker manufacturer. In addition to the circuit breaker, it is also important to consider the wiring used in the motor circuit. The wiring must be sized to carry the motor's full load current, plus any additional current due to the service factor or other factors. The wiring must also be protected from overcurrents. This can be achieved by using a circuit breaker or fuses. When selecting wiring, it is important to consider the type of insulation, the ampacity, and the voltage rating. The type of insulation must be suitable for the environment in which the wiring will be installed. The ampacity is the amount of current the wiring can safely carry. The voltage rating must be equal to or greater than the system voltage. Let's consider some common mistakes to avoid when selecting and applying circuit breakers for motor protection. One common mistake is using a circuit breaker that is too small. If the circuit breaker is too small, it will trip frequently, which can interrupt production and damage the motor. Another common mistake is using a circuit breaker that is too large. If the circuit breaker is too large, it will not protect the motor from overloads or short circuits. This can lead to motor damage or even a fire. Another mistake is failing to coordinate the circuit breakers in a system. If the circuit breakers are not properly coordinated, a fault in one part of the system can cause the entire system to shut down. Also, failing to consider the motor's starting characteristics, not considering the ambient temperature, and neglecting to properly size the wiring are all important considerations. Proper documentation and labeling are also critical for safety and maintenance. All circuit breakers and motor starters should be clearly labeled with their function, voltage rating, and current rating. Wiring diagrams should be readily available to facilitate troubleshooting and maintenance. Regular inspections and testing of circuit breakers and motor starters are essential to ensure their proper operation. Circuit breakers should be visually inspected for signs of damage or wear. They should also be tested to verify their trip settings. Motor starters should be inspected for contact wear and proper operation of the overload relays. The National Electrical Code (NEC) provides detailed requirements for the installation and protection of motors and motor circuits. It is essential to be familiar with the NEC requirements and to follow them carefully. The NEC covers topics such as motor overcurrent protection, motor short circuit protection, motor grounding, and motor disconnecting means. Compliance with the NEC is essential for ensuring the safety of personnel and equipment. To summarize, selecting and applying circuit breakers for motor protection requires a thorough understanding of the motor's characteristics, the circuit breaker's ratings, and the applicable codes and standards. By following best practices and avoiding common mistakes, you can ensure the safe and reliable operation of your motor systems. Always consult with a qualified electrician for specific application requirements. Finally, let's discuss advanced motor protection techniques. In addition to circuit breakers, there are other devices and techniques that can be used to protect motors. These include motor overload relays, motor protection relays, and soft starters. Motor overload relays are designed to protect motors from overloads. They typically consist of a thermal or electronic sensing element that monitors the motor current. When the current exceeds a preset value, the overload relay will trip, disconnecting the motor from the power supply. Motor protection relays are more sophisticated devices that provide a wider range of protection functions. They can protect motors from overloads, short circuits, ground faults, undervoltage, overvoltage, and other abnormal conditions. Motor protection relays typically use microprocessor-based technology to monitor motor parameters and make decisions about when to trip the motor. Soft starters are devices that are used to reduce the inrush current when a motor starts. They gradually increase the voltage applied to the motor, which reduces the starting current and minimizes stress on the motor and the power system. Soft starters can also provide other benefits, such as improved motor acceleration and deceleration control. Another advanced technique is the use of harmonic filters. Harmonics are distortions in the electrical waveform that can be caused by nonlinear loads such as variable frequency drives and electronic ballasts. Harmonics can cause a variety of problems, including overheating of equipment, increased energy losses, and interference with electronic devices. Harmonic filters are used to reduce the level of harmonics in the power system. Furthermore, predictive maintenance techniques can be employed to anticipate potential motor failures. These techniques involve monitoring motor parameters such as temperature, vibration, and current to detect early signs of deterioration. By identifying potential problems early, maintenance can be performed before a failure occurs, minimizing downtime and repair costs. Examples of predictive maintenance techniques include infrared thermography, vibration analysis, and oil analysis. Let's explore the integration of smart technologies for enhanced motor protection. Smart motor protection systems utilize sensors, communication networks, and data analytics to provide real-time monitoring and control of motors. These systems can provide valuable insights into motor performance, allowing for proactive maintenance and improved energy efficiency. Smart motor protection systems typically include sensors that measure motor parameters such as current, voltage, temperature, vibration, and power factor. This data is transmitted to a central monitoring system via a communication network. The monitoring system uses data analytics to identify potential problems and provide alerts to maintenance personnel. Smart motor protection systems can also be integrated with building automation systems and other control systems. This allows for coordinated control of motors and other equipment, optimizing energy efficiency and improving overall system performance. In addition to monitoring and control, smart motor protection systems can also provide advanced diagnostic capabilities. These systems can analyze motor data to identify the root cause of problems such as winding insulation degradation, bearing wear, or rotor imbalance. By providing detailed diagnostic information, smart motor protection systems can help maintenance personnel quickly and effectively resolve motor problems. Let's consider the role of arc flash protection in motor control centers. Arc flash is a dangerous electrical hazard that can occur when a short circuit creates an arc of electricity. Arc flash events can generate intense heat pressure and light, causing serious injuries or even fatalities. Motor control centers (MCC) are often the location of arc flash hazards due to the high concentration of electrical equipment. Arc flash protection systems are designed to mitigate the risks associated with arc flash events. These systems typically include arc flash relays, current limiting devices, and protective clothing and equipment. Arc flash relays detect the presence of an arc flash and quickly trip the circuit breaker, minimizing the duration of the arc flash event. Current limiting devices, such as fuses and current limiting circuit breakers, reduce the magnitude of the fault current, which reduces the severity of the arc flash. Protective clothing and equipment, such as arc-rated suits, gloves, and face shields, protect workers from the heat, pressure, and light generated by an arc flash. Arc flash studies are often performed to assess the arc flash hazards in a motor control center. These studies involve calculating the potential arc flash incident energy at various points in the system. The results of the arc flash study are used to determine the appropriate arc flash protection measures. The use of zone-selective interlocking ZSI is another advanced technique for improving motor protection. ZSI is a method of coordinating circuit breakers so that the breaker closest to the fault will trip first. This minimizes the amount of time that the fault current flows through the system, which reduces the severity of the arc flash and minimizes the damage to equipment. ZSI systems typically use a communication network to transmit trip signals between circuit breakers. The circuit breaker closest to the fault will send a trip signal to the upstream breakers, causing them to trip immediately. The circuit breakers further away from the fault will be delayed, allowing the closest breaker to trip first. Understanding the nuances of motor protection requires a deep dive into various standards beyond UL and NEC. IEC International Electrotechnical Commission standards, particularly IEC 60947 series for low-voltage switchgear and control gear, provide alternative frameworks for circuit breaker and motor protection device testing and certification. While UL standards are prevalent in North America, IEC standards are widely adopted globally. Comparing and contrasting these standards is crucial for engineers working on international projects or sourcing equipment from different regions. Furthermore, IEE Institute of Electrical and Electronics Engineers standards offer guidance on specific aspects of motor protection, such as motor starting methods, protection of medium voltage motors, and coordination of protective devices. IEE STD 141, also known as the Red Book, provides recommended practices for power distribution and coordination of protective devices in industrial and commercial power systems. These standards often delve into specific applications and provide detailed engineering recommendations. Diving into the specifics of motor protection relays is important. Motor protection relays are sophisticated devices that offer a wide range of protection functions beyond basic overcurrent protection. These relays can monitor various motor parameters such as voltage, current, temperature, vibration, and power factor, and provide protection against overloads, short circuits, ground faults, undervoltage, overvoltage, phase imbalance, and other abnormal conditions. Modern motor protection relays often incorporate advanced features such as adaptive protection, which adjusts the relay settings based on the motor's operating conditions, and self-monitoring capabilities, which detect internal relay failures. Selecting the appropriate motor protection relay requires careful consideration of the motor's characteristics, the application requirements, and the potential fault conditions. It is important to choose a relay that provides adequate protection for the motor without causing nuisance tripping. Furthermore, understanding the different types of motor starters and their impact on motor protection is essential. Motor starters are used to control the starting and stopping of motors. There are various types of motor starters, including across-the-line starters, reduced voltage starters, and variable frequency drives. Across-the-line starters apply full voltage to the motor windings at startup, resulting in high inrush currents. Reduced voltage starters, such as autotransformer starters, reactor starters, and part winding starters, reduce the voltage applied to the motor windings during startup, which reduces the inrush current. Variable frequency drives (VFD) provide the most sophisticated form of motor control, allowing for adjustable speed and torque control. VFD also reduce the inrush current and provide protection against overloads and other abnormal conditions. The choice of motor starter depends on the motor's size, the application requirements, and the power system capacity. The motor starter must be coordinated with the motor protection devices to ensure adequate protection against overcurrents and other fault conditions. Also, let's discuss the importance of grounding in motor protection. Proper grounding is essential for preventing electrical shock hazards and for ensuring the reliable operation of motor protection devices. The grounding system provides a low impedance path for fault currents to flow back to the source, which allows the overcurrent protection devices to quickly trip and clear the fault. The grounding system should be designed in accordance with the requirements of the NEC and other applicable standards. The grounding conductor should be sized to carry the maximum available fault current. The grounding electrode system should be properly installed and maintained. In addition to the equipment grounding conductor, a separate grounding electrode conductor should be installed to connect the equipment grounding system to the earth. Let's explore the use of surge protection devices (SPD) for motor protection. SPD are used to protect electrical equipment from voltage surges caused by lightning, switching transients, and other disturbances. Voltage surges can damage motor windings, insulation, and other components. SPD are typically installed at the service entrance and at the motor control center to provide protection against voltage surges. SPD should be selected based on the voltage rating of the system and the expected surge current. SPD should be properly grounded to provide a low impedance path for surge currents to flow to ground. Finally, let's talk about the importance of documentation and training in motor protection. Proper documentation is essential for ensuring the safety and reliability of motor systems. Documentation should include wiring diagrams, equipment specifications, protection relay settings, and maintenance procedures. Training is essential for ensuring that personnel are qualified to install, operate, and maintain motor systems. Training should include topics such as motor protection principles, overcurrent protection devices, motor starters, grounding, and arc flash safety. Regular refresher training should be provided to keep personnel up to date on the latest technologies and best practices. In conclusion, motor protection is a complex and multifaceted topic that requires a thorough understanding of various electrical engineering principles, standards, and best practices. By carefully selecting and applying the appropriate protection devices and techniques, you can ensure the safe and reliable operation of your motor systems. Always consult with qualified electrical engineers and technicians for specific application requirements. Remember to stay informed about the latest technological advancements and regulatory updates to maintain a high level of competence in motor protection practices.